says start recording. There we go. So I will also be recording this lecture and uploading it, be uploading it to YouTube, so you can watch it back there. This was already the last planned lecture for me to give. Kees will finish the course with you so that I can focus on automata for the last 2 weeks of that course. Kees will be providing recordings or voiceovers rather of his lectures, which will be available as soon as possible via Brightspace. So that's how we're going to cover the last few lectures of the course. Then what else? So we have lectures, we have the lab. We're trying to keep that with the similar setup that we had last week. We are aware there are some issues in delays in getting to you, but we believe it's still possible to sign you off. So we would really like to try and do that using Talkie and the queue. And finally, we're building an FAQ. So if you have any questions at all about any of the material of the course, please post them on Brightspace. Kees and I will be monitoring the forums there and trying to answer all your questions. We will collect the most frequently asked questions in an FAQ. Kees has already built quite a nice set of questions there based on his many years of teaching this course. So those are the 3 main things that I wanted to tell you about. I see Upgraders is already asking us a question. So in what week will the last lecture be given? Let me think. So the last lecture was scheduled for week 8. The recordings will be available as soon as we have them, but by the latest in week 8. And this is the last live lecture, if you will. Profis, you mentioned that it's very difficult to work together. I sympathize and I understand. You can try Talkie, as Haku is pointing out. You could try Skype, try whatever service you have available. That being said, I do still realize that's not quite the same. And therefore, if for whatever reason you believe you can't make the deadline, please send us an email. As soon as you know about this, tell us briefly why. And this is also a reason you can bring up, right? We were unable to communicate properly to do the assignment together. And then we'll look at a solution. That's all I can say about it for now. Vubero is asking us about the exam. So yeah, I also mentioned that in the email, or in the announcement. So that's indeed the 4th thing. Kees and I will be preparing an exam for the currently scheduled date. Until further notice, all we can do is recommend you prepare for taking an exam at that date. But I can imagine things have been going very fast over the past few days, right? Over the past few days. I can imagine that might change, but until further notice, Kees and I will have an exam ready on that date. And we hope that you will be ready to do it on that date. All right. I see the FAQ is currently hidden. That's interesting. It should be public. I'll make a note and I'll take a look at that as quickly as I can after during the break, maybe even, and otherwise after the lecture. FAQ is hidden, ? Yeah, thanks for pointing it out, because I'll take a look. Okay, then let's try and get this started. So, what are we going to talk about today? Yeah, even the animations seem to just be working. How very lovely. So today we will be talking, or we will be doing a quick test to start with. Then we will talk a little bit about approximation algorithms. So last week, Kees talked to you about optimization problems. And today we're going to take a look at approximation algorithms, that is finding an approximate solution and certain properties that these approximation algorithms bring. Of course, that allows us to define some new complexity classes. So we'll have one of these very nice diagrams with all the different bubbles, and we will work on that. Then we're going to take a look at some of these approximable problems, so problems for which we can write an approximation algorithm. We're also going to take a look at what that approximation algorithm is. And finally, we're going to take a look at an inapproximable problem. So if you are still working, I was going to say you might now have more or less time. I don't know how that works. But if you're still working on getting that $1 million, right, for showing that P equals NP, we're going to show you another way in which you can do that. We've already seen, of course, showing that an NP-complete problem is in P would be a good way to show that P equals NP. But now we're going to show you another way that you could use to prove that P equals NP. All right, and finally, I have some exercises, some things that you can work on, and Kees will be providing answers for that in his voiceovers of the lectures. Okay, I see that the FAQ issue has already been solved. Great. Let's take a look at the first test question. So, last week you talked about optimization problems with Kees. So now I would like to see this relation between the two types of problems. So subsum, remember what was subsum? We had a set of integers and we want to look for a subset of these integers that when you sum them together, they reach exactly a certain target T. Now we have the decision variant of that. We've shown it to be NP-complete. That means there's also an optimization version of it. Which is, okay, give me a subset that sums to exactly T. Now I want you to create a polynomial time algorithm for finding a solution to subsum, provided that we can have some sort of oracle to the decision variant of that. Now, how are we going to do this? Let's say that for the first 2 minutes or so, I'm just going to give you some time to think about it. Then I'll talk again and I'll tell you to post some answers in chat that I can discuss. So first 2 minutes, think about it. If things are unclear, feel free to ask me, but hold off on your answers so that everybody gets some time to think about it. And 2 minutes from now, I am happy to read some of your answers. See you in a bit. Okay, you should now be able to hear me again. And please, if you have some ideas, feel free to post them in chat now. Let's double check with the TAs whether you can indeed hear me again. Ah, I see answers appearing, so I guess so. Very nice answers. So the idea seems to be that we can do something similar to what you discussed with Case last week, right? Where you talked about, I think, Hamiltonian circuit. At least that's the one some of you refer to. So indeed, what can we do? We can just repeatedly try and remove one element. And if our decision oracle still says, yeah, it's perfectly possible, then apparently that element isn't needed. So here we go. Let's see. So we have an instance of our decision variant, right? Or of our problem, S and T. Then in this algorithm, I'm going to denote sub-sum is our oracle. So first, what we do is we just run our oracle. If it is a no instance, then well, already we're done. We know that whatever happens, we can't do it. So there's no point finding a solution. We just stop. Otherwise, we start with an empty set. And now we're going to do a while loop, so long as our target is still larger than 0. Right? So long as we still need to find more elements. What do we do? Well, indeed, we remove one element, which the people that answered, Blockbreaker and Picaros and Modus Wiebel and some others indicated, right? We remove the one element. We also removed from the target, and then we see, is it possible with the rest of the items to get to t minus s? And if that is possible, then we should include s, so that's the bottom if statement, right? Then s is one of the elements we need later on, so we add it, we update our target, and we go back, we continue to another arbitrary element from our set. If, however, we've taken this element out, and we ask, okay, with the rest, can we get to t minus s? And the answer is no. Well, then apparently this is not an element we want to have in our set. So we simply remove it from s, and then we continue with the next element. So there's these two options. Either, yes, we can use the rest to cover t minus s. Great, then we use this one, and now we look for a solution to the t minus s part. Or it's not possible, and then we don't need it. If we formally write that in pseudocode, you would get something like this. Right? First check, is it possible at all? If not, great, then return nothing. Otherwise, start with an empty set. If it's possible to use S and fill up the rest with all the other elements, then we add it to our solution. And we return our solution in the end. Any questions about this? I have my own stream open to somewhat gauge the stream delay to see how long I should wait before concluding there are no questions. The last thing suggested in chat seems simple, a touch different. Is it correct as well? So let me see what the last one was. For every n in S, run the oracle. So that's similar to what we're doing, right? If it rejects, it means that n must be a member. Okay, I should have maybe also... No, I couldn't have hooked up my tablet to this MacBook. Is this also correct? So my gut feeling is no. Because what we're missing here is the updating of the target, right? Yeah, so we need to make sure that we do run it with the correct target. If we take out S, then the rest of the elements need to sum to t minus S. So that's something that is quite crucial in this solution. Does that make sense, Yaniv? As for Chavez, why do we remove S from S in the loop? So we have in our loop select a random element from S, Chavez. And so we, to make sure we don't consider the same element twice, we remove it so that we cannot select it again. Does that make sense? as for Yaniv, but if they sum to t, are we still not fine? Run the oracle with... So what you're trying to do is you're trying to filter out all of the elements that are not in the solution, and therefore what you have left must exactly make the solution. Yeah, so maybe that would work. I thought about this solution when preparing, and then I came up with a counterexample, but I don't have it here. I'll get back to you on that if that's okay. So if I can find my counterexample, I'll post it on Brightspace. Good. Okay. Then let's talk about approximation algorithms. So, approximation algorithms. What is the idea? Well, let's start with a simple observation. When we have an arbitrary instance of one of these optimization problems, it's often easy to come up with an arbitrary solution. For example, in MinCover, finding just a vertex cover, not the minimum one, but just any vertex cover, is easy. What do? We just take all the vertices. In TSP, the traveling salesman problem, not sure if we've discussed it before. I haven't discussed it with you. Case might have. So TSP is the problem called traveling salesman, where you have a bunch of cities with distances between them. And what you want to do is you want to visit every city and get back to where you started as quickly as possible. So that's the optimization version. Find a simple cycle through all the cities, back to where you started, that's as short as possible. The decision version would be, is there a tour through all cities of at most length k? Right, but the decision or the optimization variant is find me the shortest one. Now again, just give me a tour, that's easy, right? Just give me a cycle, I can do that. But finding the shortest one, that's gonna be much harder. Especially since in TSP, every vertex can directly go to every other vertex. So I can just list them 1 through n. This is the order I'm gonna do. It's a tour, it's just not the smallest one. And max clique, similarly, finding a clique is also easy. Worst case, just return 1 node. It's a clique of size 1. Or return 2 nodes if there's an edge between them. It's a clique of size 2. Right? So just finding a clique, that's not hard. It's finding the maximum one that's hard. Well, this is what leads us to the following question. Given an instance of one of these optimization problems, is it possible to find a solution that comes close to the optimal solution in an efficient way? So we need to somehow talk about what this coming close means, and we need to talk about this efficient, although for the last one you probably have an idea already. So yeah, that is the question that we will concern ourselves with when talking about approximation algorithms. 2 questions about finding a cycle. Isn't that actually hard, right? Finding that tour? Well, in a regular graph, yes, it would be. But TSP normally allows us to go from any city to any other city directly. Or at least we have some sort of distance matrix from any city to any other. And in that case, it isn't hard, right? You can just take any order of vertices and you have, provided every cycle or every vertex appears once, then finding that tour is easy. I agree that for a regular graph structure, where you cannot go from every vertex to every other, yes, it would just be Hamiltonian circuits and it would still be hard. Does that make sense, Otto and Lief? Good, all right. Then, so these, that coming close to an optimal, let's see if we can be a little bit more formal about that. So, what's our idea? Well, our idea is to talk about these approximation algorithms. And we're trying to find some solution, let's call it m of x, that is feasible, which is what we denote with the f of x. I think this is notation Case introduced last week, right? So f of x is the set of all feasible solutions to a problem. So for example, for vertex cover, f of x contains all of the vertex covers. all of the possible vertex covers for our graph. Then we are looking for some solution that is, well, not necessarily optimal, but perhaps close. And then we have two things. We have opt of x, which is the cost of the optimal solution. For a vertex cover, this could be the number of vertices in a cover. And cm of x, which is the cost of the solution produced by our approximation algorithm. Then, what do we want? Well, we want some sort of performance guarantee. So, okay, we're willing to settle for a not perfect solution, right? So just not optimal, but we want to have at least some bound on it. Meaning that for minimization problems, whatever we find divided by the optimal should be bounded in some way, and for maximization, of course, the other way around. To make that very concrete, consider minimum vertex cover. We might find a cover of 8, whereas the optimal solution has a vertex cover of 4. So then 8 over 4 is 2. And we would, for instance, want an algorithm that makes sure that no matter what the graph looks like, our this ratio is always at most 2. PhonePleb, you're asking a very, very good question. What if we can't know opt? I mean, opt is the solution to an NP-complete problem, right? So how do we do that? And that's one of the most tricky things when it comes to approximation algorithms. So I'll be talking about that quite a bit in a moment, but it's really a very good question to ask, right? Because this performance guarantees depends on knowing the optimal answer. But yeah, I mean, if we knew the optimal answer, we wouldn't need this approximation algorithm. Now, please do note the following. Approximation algorithms and heuristics are really very different. So, for example, there are also NP-complete problems where you could apply a greedy heuristic. But for these heuristics, it's often the case, not always, but very often the case, that no performance guarantees can be given. So, heuristics are great, but it's much harder to find a theoretical bound on the performance. So what usually happens is they do an experimental evaluation and they say, well, for some sort of benchmark, we found that all of our solutions are at most twice as bad as the optimal ones. But for approximation algorithms, we can really show this. We can really prove this. Okay, so let's say we have an optimization problem, A. It's a member of NPO. Then we have a polynomial algorithm, an approximation algorithm for A. So we take an instance of A, we feed it to our algorithm, we find a feasible solution. Now, it will always return a feasible solution. The only thing is that it's not necessarily optimal. And then we have what we call the performance ratio. So the performance ratio is defined for a specific instance. So for example, again, let A be the problem of MinCover, right? Finding the smallest possible vertex cover. Then a performance ratio is defined for one specific instance, so one specific graph. Now, the way this is described here can be a bit tricky to read, but the way we describe it here is to ensure it works for both maximization as well as minimization problems, right? So for maximization problems, opt will be larger than our solution, larger or equal. So it will be opt over our cost. And for a minimization problem, ours will be larger or equal to opt. So it will be C of mx over opt of x. Therefore, this ratio is always larger than or equal to 1. And that's why we defined it in this weird way. It's to make sure that for both maximization as well as minimization problems, we have ratios that are larger or equal to 1. And the ground rule is that closer to 1 is better, right? Because when it's exactly 1, that means that optimal and our approximation must be equal. And as close to 1 means as close as possible to the optimal solution. Yaniv, was that the difference between heuristics and approximation algorithms? I would say yes, especially within the context of this course. Okay. So M, we then say, is an R approximation algorithm for A if for every instance the performance ratio is smaller than or equal to some value R. So for example, If we have a 2 approximation algorithm, then every possible instance I can throw in must have our algorithm will find a solution that is at worst twice as bad as the optimal solution. So this is a very important distinction. On the one hand, we have the performance ratio, which is defined for an instance. And on the other hand, we have the approximation ratio. This is this R approximation, which is defined for an algorithm. So performance ratio for an instance, approximation ratio for an algorithm. Now note that in our definition here, this R might depend on the size of X. So for larger values of X, so for larger instances, it's possible that we also have a worse approximation ratio. However, it doesn't then depend on what the instance looks like. So it might depend on the size, but not on the exact instance. All instances of a certain size will be bounded by this R. And so, yeah, we say M is an R approximation algorithm if for all X it holds true that the performance ratio is smaller than or equal to this R. And like I said, that's the approximation ratio. And that means that the approximation ratio is the smallest R for which this holds. Shouldn't we then denote this as R of X? Well, technically, yes, Yaniv, we should. Because I agree, R looks quite a lot like a constant. What we'll find is that most approximation algorithms that are actually useful, for whatever definition you want to put on useful there, actually have a constant R. That does not depend on X in any way. So for the two examples that we are going to study today, we will find they have a very fixed R. Okay. Then, the moment you've all been waiting for. Now that we've done this, we can define some approximation classes. And we're going to make a very, very, very rough distinction here. We're going to talk about approximal problems and non-approximal problems. So a problem is approximable, great word, if there is some constant approximation algorithm for it, where C is a constant. And it should still be polynomial time. Now, kind of problems that fit in this are, for example, MinCover, which we will prove later, bin packing, which you can prove for one of our homework exercises, and metric TSP, which we will also prove later today. And this class of problems, so the approximable problems in NPO, we call APX for approximable. Then we also, of course, have a set of problems that is inapproximable. So there is no polynomial C approximation algorithm for it. Examples of that include TSP, which we will also prove later today, as well as max clique. But of course, this comes with the distinction that this only is true if P does not equal NP. As soon as P equals NP, well, then TSP is just solvable in polynomial time, so surely we can also approximate it in polynomial time. We can give an approximation algorithm with an approximation ratio of 1. It will always give the right answer. And we don't have a special name for that, it's just NPO minus APX. So we have this whole bubble of NPO, we have some problems that are approximable, and we have some problems that are not. Now we can visualize that. We have P of O for polynomial time optimization. You've seen it last week. Then we have two classes, FPTAS and PTAS, that we won't go into a lot today, but they are fully polynomial time approximable and polynomial time approximal. We have APX and we have NPO. And these are the two that we will focus on today. So today we're going to focus on NPO and APX, and specifically on problems that are in APX. So we'll show MinCover is an example of a problem there, as well as metric TSP. And then we'll show that the regular version of TSP is something that is not approximable. Okay. Any questions about this so far? Yeah, so aren't approximation algorithms always polynomial? So what is the difference then between this PTAS and this FPTAS? They're good questions, Yaniv. I'm not going to go into them today. During the break, I can give you some answers about that via Twitch chat if you want, but we don't have time to fully discuss them now. So the long and short of it is that it's more restrictions on APX. Yes, so all the algorithms in APX need to be polynomial time algorithm, or to show a problem is in APX, we need to find polynomial time approximation algorithm. Yes. So APX does require polynomiality already. In CIPSR, I can't find a lot of corresponding pages. Is there more content available? Good question. So CIPSR indeed very briefly talks about approximation algorithms, but not all that much. So I'm afraid the slides are gonna have to do for this one. I think there's one other resource we link in Brightspace, but I'm not entirely sure. I'd have to check. Okay, let's take a look at our first approximable problem. So let's take a look at MinCover. So quick reminder, MinCover is the problem where given a graph, we need to find a minimum vertex cover. Well, the great thing the great thing about approximation algorithms is that it's usually fairly easy to come up with one. What can we do? We can simply try something. Just try and build some vertex cover. See if it works. So here's a first idea. How about we start with an empty cover, and then we just pick a node, any node, take it, put it in the vertex cover, and all of the edges connected to this node we remove from the graph. After all, we have now covered all of these edges. So that's what the line highlighted in red here says, right? Remove all of the edges incident with the node V that I'm putting in my cover. Let's try that out. So let's take this graph. Well, there's still edges here, so pick one. Let's pick this one. Why not? I need to pick a random one anyway. Then I've got this edge covered. Now let's pick this one. I've got these two edges covered. Let's pick this one. I've got these two edges covered. And let's pick this one. And I'm covering the last two. So my algorithm finds a vertex cover of size 4. The minimal vertex cover, however, for this one is 3, which a great animation is now showing us. So the minimum vertex cover, if you just take these 3 nodes, you've also got all your edges covered. So our algorithm, okay, it didn't find the optimal solution, but maybe this is good enough, right? Currently we have a performance ratio of 1 1/3. That doesn't sound too bad. However, okay, I'm moving ahead too quickly here. Let's quickly see that it is indeed correct. Well, every edge has an endpoint in the set of chosen nodes. How do I know? Well, that's how I removed the edge, right? So I only remove an edge as soon as one of its endpoints is chosen for the cover. And like I said, the performance ratio is 4/3. That's great, but what is the approximation ratio? So for other instances, does it perform just as good, or are there instances on which it performs a lot worse? Well, bad news on that front. This algorithm is a pretty bad idea. And why is that? Well, take the following graph, a graph that we call a star graph. It looks like this. We have one node in the middle, and now we have n nodes around it. And the node in the middle is connected to all these other ones. Well, our algorithm is just going to take random nodes. So worst case, it's going to pick all of these nodes on the outside to cover all of these edges. And therefore, our algorithm might choose n nodes. But the optimal choice is to just take the one node in the middle. So what does that mean? Well, for very large n, that means that, or not even for very large n, but just in general, that means that our worst case performance ratio is n. And so our approximation ratio is also ON. And that's not great, right? Because that means that as the graph grows larger, it's possible that our solution becomes worse and worse and worse and worse. Rather than being 20% worse in all cases, we could now be n times as bad. Now the Nick is giving us a very good suggestion here. Okay, so let's solve that. How about we simply prioritize the highest degree vertices, right? How about we make sure that this scenario cannot happen, and we start by picking the node with the maximum degree. Yeah, Noah is suggesting the same thing. Let's try it, right? It's a good idea. So let's see if it works. So instead of picking a random edge, picking a random node and removing all of its edges, now we pick the node with the highest degree and remove all of its edges. Again, let's see how that works. So, okay, I've picked one. Now I need to pick 3 more. Right, so the first one covers the 3 edges on the left, and then I pick the 3 on the right, because they now have an equal degree. So removing or taking the vertex on the left removes the edges on the left. Therefore, it's equal to pick whichever other one I want. And then, well, I have a solution. The optimal solution, however, can do it with just 3. And on this instance, again, the performance ratio is 4/3. Now, how do we compute the approximation ratio for this algorithm? Well, it's a little bit trickier than with our previous one. It's not just a star graph, but I can still show you that although this idea was a very nice idea, unfortunately, it's still not going to work. So let's take a look at the worst case example. Well, for starters, I'm going to create a bunch of these edges, edges with just 2 nodes, right? So pairs of nodes, if you will. Let's call them R1. Let's say there's n of those, and now I also have R2. That is, and there's n over 2 of those, and they are connected to the first 2, and then to the second 2, and then to the third 2, and then to the fourth 2, and so on and so forth. And now I have R3, which is going to be connected to the first 3, the second, and so on and so forth. Let me just show it to you here. And why do I do this? Well, I do this to ensure that everything in R1 has a degree of exactly 1. Everything in R2 has a degree of exactly 2. Everything in R3 will have a degree of exactly 3. And in Rn will have a degree of n. Now, what does that mean? It means that our algorithm is going to choose all of these R nodes, because the one on the right is going to have the largest degree, so it's going to start with that one. And then there's degree with n-1, so it's going to pick those. And then there is with a degree of n-2, so it's going to pick those, and so on and so forth. So that means that there is n log n things that the algorithm will pick, but the minimum cover is just taking these L nodes at the top. And, well, these L nodes, or these nodes in L, that's n nodes. So our minimum cover has only n nodes. So we have n log n divided by n. We have an O log n approximation ratio. Quite a lot better than what we had before, right? Where our approximation ratio was ON. But now we have O log n. Now, how do I know that this is the worst case? And also for the previous one, how do I know it's the worst case? It's a good question, Davater. There are, let's say, there are ways of proving this, which require you to show that the bound of this would be O log n, and then this is what we call a tight example. But to do that for, let's say, these bad algorithms, right, the ones with non-constant approximation ratios, doesn't really make sense, in the sense that these algorithms are ones we tend not to use. So what we'll do is I'll show you how we can do this for our third idea, the last one, because that one has a very nice constant approximation ratio. So for that one, I'll show you how we can prove that, and then we also show a worst case example for that. So Ahmad is also asking something similar, right? Is finding the worst case the only way to find the approximation ratio? It's always a combination, but I'll discuss that when we have one of these constant approximation ratios in a moment. Now, what am I going to do? We have about 1 minute left before it's break time, because yes, even in this setting, we will of course just have our 15-minute break. I'm going to introduce the algorithm to you, and then we'll have a short break. So, what's going to be the idea? Well, instead of choosing a random vertex, we're going to pick a random edge. And then for that edge, we're going to add both of its endpoints to the cover, and we're going to remove all of the edges that are now covered by these two vertices. So there's a very nice mathematical way to describe that, but in plain English it just says remove all the edges from E that are incident to either U or to V. So all we've done is, instead of taking a random vertex, we take a random edge. And as it turns out, this is enough to show that we have a constant approximation algorithm. If you want, you can spend the next 15 minutes already trying to see if you can prove for yourself that this will indeed be a good approximation algorithm. Alternatively, you can get a fresh cup of coffee, stretch your legs a bit, and I'll see you back in 15 minutes. If you have any questions, I will try to stick around in Twitch chat to answer some, though I also want to get some new water for myself. See you in a bit. Right. So let's try and get started again. Quick check to make sure I've configured everything properly and you can hear me again. Like I mentioned in chat earlier today, OBS and Keynote kind of hate each other, so it's not really possible for me to check that. Okay, good. It seems to be working. Osuka, I'm just sitting in my behind my desk at home. So yeah. Okay, good. Then let's get started again. So we have seen two ideas for an approximation algorithm for MinCover that unfortunately don't work. One had an approximation ratio of at least ON and one of O log n. Now let's try this first idea. So the idea was pick an edge at random and take both of its endpoints and put them in our cover. Remove the edge, remove all of the incident edges to U and V, and continue. Again, let's apply it first. So let's pick a random edge. Let's pick this one. That means we add these two vertices to our cover. Then we remove all the edges connected to them. Now we pick another edge. Let's say we pick this one. And we add both these vertices. We could remove all the other edges and we're done. Performance ratio 4/3. Because remember, the MinCover for this instance was of size 3. Okay, so that's the algorithm, right? Pick a random edge, put both of its vertices in the cover, remove all of the incident edges. Continue. Well, let's see how this algorithm performs. First, let's show that it's correct, right? Perhaps not unimportant. Well, we want to make sure that we have a cover that covers all the edges. An edge is removed if it has a representative, namely when X and or Y is in our cover, because we only remove edges that are incident to vertices we put in our cover. So when our set of edges is empty, then for every edge we must have a representative in the cover. So it is indeed a vertex cover. Now let's try and see the more difficult part of this. Let's see if we can show that it has a certain constant approximation ratio. So let's see. What does our algorithm do? Well, every step we put a pair of nodes in our cover. Now, this cover we call C. Let C of E be the set of edges that we've taken, right? So the set of edges that were randomly picked. Then what do I know? Well, the set of edges is exactly half the size of the set of vertices in my cover, because every edge puts exactly 2 vertices in my cover, and I know that all of these edges that I picked don't share any nodes. Why? Well, because when I pick an edge, I remove all the edges connected to these 2 nodes, so there's no way I can pick this node again, or these nodes again. So every edge has at least one unique vertex in the optimal cover as well. Right? So I know I'm picking exactly half, or the number of edges is exactly half of the number of nodes in my cover. And these edges that I picked all need to be covered by a minimum cover, by any vertex cover, and therefore one of their endpoints, which are all distinct for these edges that I've selected, must be in an optimal minimum cover. So this set of edges that I've picked, which was half the number of vertices that I picked, must be smaller or equal to the minimum cover. And therefore, just swapping them over, the size of our solution divided by the size of the minimum cover is at most 2. And Otto, indeed, so you're asking, right, we have this non-determinism in our algorithm, like take an arbitrary edge. So could there then not be multiple performance ratios based on what if we take bad edges? Well, it's a very good question, and we'll talk about it a little bit when we talk about probabilistic algorithms next week. Or rather, when you listen to case recordings of that. But for our approximation algorithms, we indeed consider the worst case, as the block breaker and Yaniv both point out. So yeah, in this case, we are at worst twice as bad as the minimum cover. Now that's great, but perhaps in our theoretical analysis here, we're being very sloppy, right? So we have an approximation ratio of 2, but what we want to show is that this bound is also tight, meaning that there is a specific instance for which the performance ratio is exactly this 2. Because remember, approximation ratio was the smallest value of R for which this would be true for all instances. And maybe it turns out that, okay, it's always smaller than 2, but maybe it's always smaller than 1.5 as well, right? So now I want to show that there is an instance which has a ratio of 2 to show that 2 is indeed the smallest we can get it. Now let's build that instance. And it's actually a fairly simple instance to construct. Simply consider a whole bunch of pairs of nodes. That's it. Why? Well, our algorithm is going to select a random edge, okay, and it's going to add both of the vertices. However, the minimal vertex cover will just pick one vertex for every one of these edges and has a size of n. Ours will pick both for every edge and so has a size of 2n. And so indeed this is an instance with a performance ratio of 2n over n is 2. So we have done two things. On the one hand, we've shown that no matter what the instance looks like, the performance ratio must be at most 2. And now we have one for which it is exactly 2. And that together allows us to conclude that we have found a 2 approximation algorithm for MinCover. And the algorithm is fairly simple, namely pick a random edge, put both its endpoints in the cover, remove all the edges you've now covered, continue. So how do we know there are not cases worse than 2, Noah? That's because of our proof of the approximation ratio. So we've reasoned that by the edges we select, by the edges we select, they all have unique endpoints. And so that means that one of these endpoints at least must be in the minimum cover. And so we can say that the size of the stuff we've selected must be at most the size of the minimum cover, and therefore some rewriting shows us this cover, the ratio of 2. So the block breaker, so we create both an upper and a lower bound. Yeah, that's a way to think about it. Indeed, we have one specific instance that shows, well, there is one of 2, and the other says, well, it's at most 2. So together that means that 2 is the smallest one we can find. And Otto asks, is it also possible for n equals 1 to give this as a counterexample? And yes, it is, because then we have 2 versus 1, and 2 over 1 is 2. Okay, a 2 approximation. Well, that's very nice. Could we do better? Well, people have been working on this for some time. And in 2004, someone showed that it's not possible to create a 1.36 polynomial approximation algorithm unless p equals np. You might think that's awfully specific, right? How did they get to this? Well, I'll show you a completely different example later on that shows that a 2 approximation algorithm for another problem cannot be created. And similar techniques have been used to find this 1.36 bound. But quickly after that, someone put down a conjecture, and this conjecture still holds true, though it's not been formally proven. But we now believe that there is no epsilon larger than 0, so that there is a 2 minus epsilon polynomial approximation algorithm for MinCover. So we believe that the algorithm we've just seen is the very best we can do. Unless, of course, p equals np. because at that point minimum cover can just be solved in polynomial time, therefore we can approximate it in polynomial time. So far then for MinCover. Let's take a look at metric TSP. Metric TSP is the traveling salesman problem, which means that there is a set of cities and some distance function. Between a pair of cities there is a certain distance. But we have two extra criteria on metric TSP compared to regular TSP. On the one hand, we have the constraint of symmetry. Traveling from S to S prime takes exactly the same distance as traveling from S prime to S. Furthermore, we have the triangle inequality. What does that mean? It means that going along two edges of the triangle will always take you more time than the going directly from these two ends. So going via another point somewhere will always be longer than going there directly. Yaniv, I see a question about the slides on Brightspace. There's always a colored and a non-colored version, or at least that used to be the case. I'll be uploading a colored version in which you should be able to see the notes as well. So metric TSP, regular TSP with two additional constraints, symmetry and the triangle inequality. And now the question has remained the same. We're looking for an optimal tour, i.e. a way to go through all the cities, such that the distance of that tour is minimal. Example instance, here's a bunch of cities. We can go from any city to any other city directly. And we have this triangle inequality. So for a random triangle, I've taken one here. We know that going from, does my mouse show up? No. Okay, so going from E to H, and then from H to F will take us longer than going directly from E to F. Right, this is one of the extra constraints in metric TSP. Now let's find an approximation algorithm for this. Let's construct a minimal spanning tree. Hey, we know how to do that. We learned that in ADS and algorithm design. We can use prim or Kruskal or whatever we like. Anyway, we can do so in polynomial time. So construct a minimum spanning tree. Here we go. And like I said, we can do that in polynomial time. We even have a nice reference to the exact page in the book if you want to look it up again. But we can do this. Now I want to show to you that I can use this minimum spanning tree to construct an approximate tour. A tour that is at most a constant as bad as the optimal tour. How am I going to do that? Well, I'm first going to conclude the following. This minimum spanning tree that we have can have costs no larger than the optimal tour. How do I know that? Well, consider that we know the optimal tour. Now remove one edge from that tour. Then we have a minimum spanning tree. We have a spanning tree, not a minimum spanning tree, but we have a spanning tree. After all nodes are now connected, right? If we have a tour, so we have a cycle, but I just leave out, for example, the last edge, I still have a tree. It's a very stupid tree because it's just a list, but I have a tree of all of the nodes. And it's a spanning tree, it connects all of them. But the way I've taken this one is that it is a minimum spanning tree. So whatever else costs this tour must have, they must be at least the costs of my minimum spanning tree. And in fact, I'm adding one more edge to it, so definitely at least that. Okay, so the costs of our spanning tree must be smaller than the costs of our tour. What's next? Now I'm going to use this spanning tree to construct a semi-tour, the thing that will eventually be our answer. What do? Well, I simply use every edge from the minimum spanning tree twice. So we're drawing it here. There we go. So we start in A, we go to B, to C, to D, to E, to F. And we use every edge twice, so we go there and we go back. Now, this isn't quite a tour yet for TSP, because in TSP we're only allowed to visit every city once, but trust me, we'll get there. So this is our first step in creating such a tour. Now, again, something to observe. The costs of this semi-tour that I've created are exactly twice the costs of my MST, so they are at most twice the cost of the optimal solution. Remember, because the MST was smaller than the optimal solution, so if I have 2 times the cost of the MST, then I have something that's smaller than, or that's at most 2 times the cost of the optimal solution. And now let's turn this semi-tour into a proper tour. So we're going to remove double visits by using shortcuts. For example, this first one, from B to C, from A to B to C, I'm just going to go from A to C directly. And thanks to the triangle inequality, which Chavez is not something we need to prove, so Otto and Yannick were quite right. This is an extra constraint upon our metric TSP problem. So everything we're doing here only works for graphs in which this triangle inequality as well as the symmetry properties hold. So it's a constrained version of regular TSP. So for metric TSP, we can remove all of these double visits by using these shortcuts, and the triangle inequality says that, well, going from A to C directly must be smaller than going there via B. We can do this for all of them. So here's another one. We can replace that. And there's another one here. We can replace that, right? We're just doing the same trick twice. And so in this way, I need to click quite a number of times here, we can get rid of all of these double visits that we were not allowed to have. There we go. And now, after removing all of these double visits, we found a tour. And that means that the costs of the tour, well, thanks to the triangle inequality, they must be smaller or equal to the cost of the semi-tour that I had. And the semi-tour was twice the cost of the MST, and the MST was at most the optimal solution. Therefore, whatever costs this tour has that I have constructed must still be at most twice the cost of the optimal solution. So we have found a polynomial algorithm that constructs a tour such that the cost of that tour are at most twice the optimal solution. Questions about this? Notice that now we've only shown the upper bound again, right? We are still going to have to look for that tight example to show that it really is 2 and not actually 1.5 or something else. But it is at most 2 now. Okay, so there are indeed some questions. So this is at worst 2 times. Yes, Yannick, this is at worst 2 times. How does the triangle property hold for B, C, G, and I? So let me go back a bit. Right. So what we're basically doing here is applying the triangle property twice, Utoge. So we could first remove G by going from I to C directly. And this must be smaller than going there via G, thanks to the triangle property. And now we can say, okay, but going from I to B must be shorter than going from I to C and then from C to B. again, thanks to the triangle property. So I'm basically doing it twice in one step, if that makes sense. Otto asks, are we going to show correctness for this? Which might not be trivial. Let's see if I have it on my slides. I don't think so. But an MST covers all of the, or spans all of the nodes in the graph, right? So we are guaranteed to visit all of them. So by doing this double tour, or using all of the edges in the MST twice, we must be guaranteed to visit all of the nodes. And by removing shortcuts, well, we still make sure that we visit every node at least once. And indeed, how do we determine what nodes to skip or which shortcut to take? Well, we could indeed just start by taking, so if we go back a couple of them here, we start by observing, well, A is going to be our randomly chosen start node, so it's okay that we visit it twice because we need to start there and end there. And now the first city that we go to, B, happens to be on the path twice, so that's the first one we remove. And we repeatedly do this, right? So we add this one, and now D is the next one that we visit twice. So we make sure that we take care of it, or we even visit it 3 times. So we first remove its second visit, and now we remove its third visit. And in doing so, also remove the one to C, and so on and so forth, right? So basically, as long as there is a node that we visit multiple times, we take a look at the 2 vertices next, the one it comes from on that second visit and the ones it goes to, and we connect those directly instead. Does that make sense, Ultra Timon? Great username to pronounce. Yeah, and how do you determine what nodes to skip? So we could just skip one every time, then we just need to do this trick a couple more times. Because when I skip more than one, I'm essentially just doing the same thing twice. Alternatively, as much as you can, Yaniv, yeah, sure, that would work too. So you can do it one at a time and just do it a couple more times than I did it. Both are going to work. Okay. Then, let's take a look at that tight example. So for our tight example, consider a graph that's both a star graph, but also a cycle. So it has this node in the center that's connected to every other node, and all the nodes on the outside are also form a nice cycle together. Now, let's say that these edges that I've drawn all have a unit cost, so a cost of 1, and all of the other distances have a cost that is just computed by shortest path, right? So going from the top one to the bottom one, for example, has a cost of 2. Now, the triangle inequality holds here. How do I know? Well, they are triangles when I just draw it on a piece of paper. The length of the minimum tour in this one is n. Because what can I do? I start from the center, I go up, I follow the outside, and I go back to the middle. Yeah, take a second to convince yourself that indeed there is no shorter path. An easy way to perhaps convince yourself is that if there are n nodes, and all the minimum distances between 2 nodes are always 1, then it's definitely impossible to do it better than going or having a total distance of n. Now, take a possible MST, for example, the star. Now construct the semi-tour using this star. It's not pretty to look at, but this is what it looks like, right? We go from the start, from the center, we go to 1 on the outside, and then we go to 2 on the outside, and then we go to 3, and then we go to 4, and so on and so forth. And the problem here is that we visit non-adjacent nodes, right? So first we go to 1, and then we go to 2, and then we go to 3, and then we go to 4, and then we go to 5, and then we go to and so on and so forth. Every time they're non-adjacent. Therefore, when we do our little trick to remove all these shortcuts, or take all these shortcuts, we do something like this. Again, it's not a pretty sight, but it is a tour. And all of these shortcuts are going to have a length of size, or there's going to be n minus 2 times that we take a transition of size 2. And there's two paths of length 1. Add those together, 2n minus 2. Well, the optimal solution was n. When we divide 2n minus 2 by n, yeah, we get 2 minus 2 over n. So for very, very, very large n, when n approaches infinity, we get indeed our performance ratio of 2 for such an instance. Right? Give me whatever number smaller than 2 you give me, and I can give you a number n such that the performance ratio is equal to that number slightly smaller than 2. So indeed, this forms a tight example. So Chavez, indeed, Otto is right. I agree, it looks similar to Hamiltonian circuit, but we're not asking, is there a circuit, but what's the shortest circuit? And the graph is indeed fully connected, so I can go from any city to any other city directly, meaning that the question, is there a tour, is trivial to answer. Yes, there is. Take any order of nodes, and that's a tour. So the question is, what's the smallest one? And Yaniv, it can never perform worse than twice as bad. And now we have an instance for which we have a performance ratio of exactly, well, of 2 in the limit. So that's enough to conclude that we have this 2 approximation. Right? It's never worse than 2, and we found one that is at that edge. So it can never be 1.5, for example, because this would be our counterexample. Right? There might be other instances for which it even gives us the correct answer. There might be instances for which it gives us 1.5 times the optimal solution. But there are also instances, namely at least these unions of stars and cycles, for which it might give us a performance ratio of 2. And therefore the approximation ratio is also 2. Right? So there could be instances for which it performs better. So it's not always at least times 2. Just for these graphs it is possibly 2. Exactly. Picros is right. Yeah, the second statement should be there are instances for which it has to perform at least 2. Yeah. Okay. Last thing I want to discuss is an inapproximable problem. So we've just taken a look at metric TSP, which was TSP with extra criteria. Now let's take a look at regular TSP. So regular TSP is just we have a set of cities, we have distances between them, find me the shortest tour through all of the cities. Now, what do I want to do? I want to show to you that this problem is inapproximable unless P equals NP. So what am I going to do? I'm going to show that if TSP were approximable, then P equals NP. So finding an approximation algorithm with a constant approximation ratio is just as hard as proving that P equals NP. So here we go. Assume that we can solve TSP with, or that we can approximate TSP with a polynomial R approximation for some R. Right, so we apply our approximation and we find a solution that has most R times as bad. Optimal is smaller than ours, and that's at most R times optimal. Now I'm going to show that under this assumption, right, under the assumption that it is approximable, I can make a reduction from Hamiltonian circuit to this TSP so that I can decide the Hamiltonian circuit problem using this approximation algorithm M. And if I can do that, well, then I have a polynomial time algorithm to decide a problem in NPC. Therefore, P would equal NP. So starting with the assumption that we can approximate TSP, I'm going to show that we could decide Hamiltonian circuits. Let's see. Here's the example we will be using. First thing we're going to do is all of the edges that exist in the Hamiltonian circuit graph, we will also have in the TSP graph, and we give them a length of 1. But TSP requires all nodes to be connected to each other, so we also add all the other nodes, or all the other edges, but they have a cost of a certain constant A, where we pick A to be this, R times N plus 1. So R is this approximation ratio, right? Remember, we started by assuming that we could approximate TSP opt within some approximation ratio R. In our reduction, we're making use of the fact that this algorithm exists. We're using this R. Now, consider two scenarios. Either our Hamiltonian instance, our Hamiltonian circuit instance, is a yes instance. If it is a yes instance, then I can find, or then the optimal tour would have a length n. After all, I can only use edges of length 1 to construct this tour, right? Hamiltonian circuit says there is some tour, so TSP will say, okay, well, the smallest one I can find is by taking all of these ones. But I have an approximation algorithm for it, so my approximation algorithm might be wrong by a factor of R, so it will give me a solution that is at most R times N. Right, so the cost of my solution, yeah, I should have looked into getting a pointer working or something, but my mouse doesn't show up on the other screen. The cost of my solution is R times the optimal, so at most R times the optimal solution is at most R times N. Now consider a no instance of Hamiltonian circuit. If it's a no instance, then it's not possible to construct a tour consisting of only these ones. We need at least one in there that has a cost A. So the cost of this of the optimal tour is then at least n minus 1 edges of cost 1. Sorry, this side for you. N minus 1 edges of cost 1. And at least one edge of cost A. So of cost R times N plus 1. The X is a bit confusing there. It's meant as the multiplicative symbol. So I should have replaced it with a dot, right? R times N plus 1. Because N minus 1 edges, maybe we can have of cost 1, but there must be at least one edge that was not present in the original Hamiltonian circuit instance. So at least one edge of cost A. Well, if we add these together, that's R plus 1 times N. So the cost of the algorithm, or the cost that the algorithm find, is larger than R times N. And that means that if it's a yes instance, it's at most R times N. If it's a no instance, it's at least R times N. Or actually, it's strictly larger than R times N. That means that if we have this polynomial time approximation algorithm, then we can decide Hamiltonian circuit. Because what do? Well, I reduce Hamiltonian circuit using this reduction. I use my approximation algorithm, and I look at the answer. If the answer is smaller than or equal to R times N, then great. It must have been a Hamiltonian, it must have been a yes instance. And if it's larger than R times N, it can't have been a yes instance. So TSP in opt being approximable is a way to show that the decision variant of Hamiltonian circuit is decidable in polynomial time. In other words, TSP opt being in APX means that Hamiltonian circuit is in the intersection of NPC and P. Therefore, TSP in opt implies P equals NP, and therefore TSP opt is not in APX unless P is not equal to NP. So if you want your shot at getting that $1 million, right, for showing that P equals NP, here's an alternative path for you. Instead of taking an NPC problem and showing that we can solve it in polynomial time, you can focus specifically on this problem, and there's some others like it, and show that we can approximate this problem in polynomial time. You don't need to solve it exactly, just find us an approximation in polynomial time with a certain guaranteed upper bound, and you've also shown that P equals NP. It's perhaps a nice alternative proof method to consider. Any questions about this proof that TSP opt is not approximable unless P equals NP? You are quite right, Yaniv. This does not apply to the metric TSP because as soon as we put these two extra constraints on it, right, symmetry and triangle inequality, then we do have an approximation algorithm. So this is only true for the general TSP problem. The given instance here is a no instance. We cannot find a simple circuit through all the nodes, Timon. Otto, is the slide wrong? It says TSP opt not in APX unless P does not equal NP. Shouldn't TSP opt not in APX imply P equals NP? No, so if it is in APX, then P does equal NP. And now we're saying the unless is a bit tricky, but it basically means if P does not equal NP, then TSP opt is not in APX. Right, so the unless is basically if. So TSP opt is not in APX if P is not NP. And that's the contrapositive of the top one. I don't think the unless should be implies. No, so we have the first statement. TSP opt in APX implies P equals NP. Now take the contrapositive of that. That says P does not equal NP, implies TSP opt is not in APX. And a different way to write that is TSP opt is not in APX unless P is not in NP. So the second, okay, the first is this, and the second is I'm typing it in chat now because I feel that might be easier than saying it again. I see other people are also typing it in chat. Oh, enter doesn't work. Okay, great. Yeah, if you read unless as if, then it should work. That's at least what we meant. I can update it to read if before uploading the slides. That, I agree, makes more sense. So why does this not apply to MTSP? Because the reduction we are using here, Yaniv, so the reduction that's currently on the slide, doesn't have the triangle inequality. Right? Consider, for example, going from the node all the way in the bottom to the node in the top right. It is faster to go via the node on the right than it is to go there directly, because 2 will, well, for n larger than 1, still be smaller than a. So the reduction we have here doesn't work, and we have not been able to come up with a reduction, we have not been able to come up with a reduction that would work for the metric TSP problem. So is a larger than 2? Well, a is equal to r times n plus 1. R is at least 1. So yes, pretty much for any value of n at least 1, this is going to be larger than 2. Okay, that leaves me with 4 minutes to give you 2 exercises to think about if you like. First, bin packing. So we had this idea of bin packing, right? We have a set of items, and I want the smallest partition, or the smallest set of containers to store all of these items. How does that work? Well, now I'm going to give you an approximation algorithm for this. So start with an empty container, select any random item. If there's space in this container, put it in there. Otherwise, ignore it, start a new one, and start filling that one up. I'd like you to find the approximation ratio of this algorithm. Is it good? Is it bad? Is it constant? Is it not? That's the first exercise. So just bin packing is, here's a set of items, all with a weight of at most 1. Put them into containers with capacity 1. What's the smallest number of containers we need? And this approximation algorithm, I'd like you to find the approximation ratio. Second exercise, we have subsum. We've talked about it today, right? I'd like you to construct a 2 approximation algorithm for subsum. You may assume 2 things. You may assume that all of the items that are available to us have a weight that's smaller than the target. So they could potentially be included in a solution. And the target is also, I shouldn't say reachable, because that might imply it's a yes instance, which we don't know. But the sum of all of the items is larger than the target. So T might be reachable. So these are subsum instances, and we're specifically looking at the subsum opt problem, but the instances for subsum and subsum opt are the same, right? The instance is the same, the question we ask is different. And a second hint, and this is where all your algorithm design senses should start tingling, is to first sort as decreasingly. That's the second exercise for you to work on. Now, let me answer 2 last questions in chat on stream, and then I'll stick around for 5 or 10 more minutes in chat to answer any questions there, if there are any. Will this exercise be discussed by Kees? I presume so. So he's recording voiceovers for the last few weeks of lectures, and I think that he will also discuss these exercises. Yes. 2 approximation means R is 2. Is that right? Yes, that is right. And I'm curious about this one. Can we decide Hamiltonian cycle on a triangle graph? Boom, boom, boom. Let me think. So that's the other way around, right? I'd say no, because Hamiltonian cycle isn't about distances in any way. So an extra property about the distances isn't going to matter. Can we decide Hamiltonian cycle on a fully connected graph? Yeah, for sure. Because in a fully connected graph, the answer is always yes. But can we decide it on a triangle graph? I don't think so, because of this extra restriction that we don't do anything with distances. Picros, I'll answer your question in chat in a moment. I'm going to wrap up here first because I see we've reached the end of time. End of time sounds very dark. The end of the lecture. So this was my last lecture for the course. I will see you whenever the exam of this course will take place. If you missed the first few minutes of this stream, I don't know yet when that will be. We are awaiting official Delft regulations. In the meantime, Kees and I will be preparing an exam for the date that is currently in the schedule. And we suggest you also start preparing to take an exam on that day. I hope to be able to see you there then, but we'll see how things go over the next few days and weeks. And I'm sure I'll see you at some point in the future. But this has been my last lecture to you, I think. Which means that, yeah, this was it. See you around.